Today we're going to be talking a little about properties of waves. I drew here a transverse wave. On any type of transverse wave, the top point of the wave is known as the crest, and the bottom point of the wave is known as the trough. The midpoint of the wave I'm going to draw in with a dotted line, and the distance from the midpoint of the wave to either the crest or the trough is known as the amplitude of the wave. Wavelength is the distance between a point on one wave and the same point on the next wave. Generally, it's easiest to go from crest to crest or trough to trough. So here I'm drawing in the wavelength, and wavelength is given the Greek letter lambda. Frequency is the number of cycles per second. A cycle would be from here to here. This is one cycle. From here to here is a second cycle, and from here to here is a third cycle. We know that this takes 3 seconds, so we have 3 cycles in 3 seconds. So the frequency of my wave is 1, and it is 1 cycle per second, or 1 hertz, Hz. The last thing that we might want to know about this wave is the period. And the period is the time required for just 1 cycle. And if 3 cycles took me 3 seconds, then I know that 1 cycle from here to here would take 1/3 of a second. So the period of my wave is 1/3 of a second. Knowing wavelength and frequency, we can calculate wave speed. Wave speed is simply how fast a wave travels. Wave speed, given the variable v, is equal to wavelength, given the variable lambda, times frequency. For physical science, will be given the variable f. Technically, frequency uses the Greek letter nu. Knowing this, we are now able to calculate speed. For our purposes, wavelength will always be in meters. Frequency will always be in hertz, which is the same as cycles per second. Therefore, wave speed will be measured in meters per second. A previous calculation may need to be given if you're given the period of the wave. Period is just 1 over frequency. The inverse of that is also true. Frequency would be equal to 1 over the period. You may see this equation written this way. Instead of a v, c equals lambda, frequency. C is the speed of light and works for any light wave as well as any wave on the electromagnetic spectrum. And the speed of light is 3 times 10 to the 8th meters per second. Let's try an example problem. I want to find the wavelength of a wave on a spring that has a period of 2.1 seconds and travels at a speed of 6.8 meters per second. I'm given that the period of the wave is 2.1 seconds and the speed is 6.8 meters per second. And what I want to find is wavelength. Before I can go and calculate wavelength, I need to know the frequency. Frequency is 1 over the period. So frequency is going to be 1 over 2.1 seconds. So my frequency, which I can add right to my data, is going to be 0.48 hertz. Now that I know that, I can go to solving for wavelength. Wavelength is going to be equal to speed divided by frequency. Wavelength is going to equal 6.8 meters per second divided by 0.48 hertz. And overall, my wavelength is going to be 14.2, and the unit on wavelength is meters. For our next problem, we're going to find the frequency of a light wave that has a wavelength of 4.9 times 10 to the negative 9th meters. So I'm setting up My wavelength is 4.9 times 10 to the negative 9th meters, and I'm looking for the frequency. Recall that this is a light wave, so it travels at the speed of light, which is 3 times 10 to the 8th meters per second. Frequency is then speed over wavelength, so my setup is going to have 3 times 10 to the 8th meters per second divided by 4.9 times 10 to the negative 9th meters. When you do that out, the frequency of this wave is going to be 6.12 times 10 to the 16th, and our unit of frequency is hertz. If I wanted to keep going here, I could find the period of this light wave by doing 1 over the frequency, and the period would be 1 over 6.12 times 10 to the 16th hertz. And so the period of this wave would be 1.63 times 10 to the negative 17th, and our unit on period, due to frequency being cycles per second, would be seconds.